All right, I've graded the second midterm and posted the scores. And I'll post the key here in a little bit. Here's a quick run over the key. All right, so this is a pressure vessel on number 1. The hoop is PR over T. So just multiply that out, you get 750,000. The axial is P over 2T, which would be 375,000. The hoop splits the tank along the long axis, so it's sigma Y. The axial then tears the ends off the tank, so it's sigma X. The maximum normal stress is just the hoop, it's 750,000. To find the stress on plane AA, you just use the normal stress formula. The angle you want to use there is 72 degrees, measured counterclockwise from the vertical plane. So that's equation 75. Tau xy is 0. Plug in sigma x, sigma y in the angle, and you'll get 714,191 newtons per square meter. All right, to find the maximum shear stress in the tank, the formula to use on that is formula 30. Tau max is plus or minus sigma max minus sigma min over 2. Sigma max is the hoop at 750,000. Sigma min, what we're going to do here, we're going to use the out-of-plane shear stress. So sigma min would be sigma z, which normally is 0, and you could have used that. You could also use the internal pressure, which is like a compressive stress, so negative 12,000. So either put 0 or negative 12,000 there. So you get 381,000, or if you use 0, you'll get 375,000. So that's the maximum shear stress in the tank wall. Okay, the next one there, we're going to use Hooke's law to find that, and a little bit with this formula here. The final length is the original times 1 plus the strain. Okay, just find the stresses in the XY directions. There's the normal and shear stresses. Plug into the Hooke's law equation. That's equation 41. Epsilon x is negative 0.2125. 1 minus that times the original length for BC, which is 5, will get you 3.94 centimeters, basically. Epsilon y, you use this formula. That's formula 42, I think. When you plug everything in, you'll get 0.1708. So 1 plus 0.1708 times the original 6 gets you 7.025 centimeters. That's the length from A to B, the new length from A to B. The final angle is based on the shear stress divided by G, which gets you the shear strain. 0.23, that's an angle in radians. It's positive, so the angle gets smaller. So take the original 90-degree angle, pi over 2 minus the shear strain. That'll get you 1.3408 radians. Convert that into degrees. The final angle is 76.82 degrees. Okay, the next one here, you want to get the shear strains in the X and Y directions. So negative 0.04, or excuse me, positive 0.04 for the X, negative 0.022 for the Y, and the gamma XY is a positive shear strain because the angle gets smaller, so that's 0.018. So to find the shear strain on FG, you just use the biaxial shear normal strain formula. So this is, I might have misspoke there, this is to find the normal strain on FG. Okay, so to find that normal strain on FG, use the normal strain biaxial formula, equation 71. The angle to use there is 32 degrees because the angles for strain are measured from the horizontal. Plug all this information in, you get a strain of 0.03068. The shear strain on angle EFG, again, is based on the 32-degree angle. You use formula 72 for biaxial shear strain, and you'll come up with negative 0.0478. Okay, the next problem here, you're given the normal strains in the X and Y directions, and the shear strain, you assume that half the shear strain acts on each side. B is our reference point. We've got 10 centimeter long lines on either side. So what I've done there is I've marked off with these hatch marks a strain that would equal 0.1. So I've broken up each line into 10 equal parts. So between the two hatch marks, which is two small boxes, represents a strain of 0.1. So epsilon x here, negative 0.15. So that's 0.1 there. Half, again, more will get you 0.15 negative. So that point C is moving in towards B. Half of the shear strain would get you basically what's the alpha angle. That's minus 0.12. Negative means the angle gets bigger. So we're going to go down two little boxes for 1, a little bit more for 0.2. There's the final position of C. Same sort of deal for A. A gets longer by 0.1, that's 2 small boxes, and kicks out 0.12 to end up at that final position there. Okay, the polar moments of inertia, pi over 2 r to the 4 for this one, pi over 2 outer radius to the 4 minus inner radius to the 4 for this one. You can use these values throughout the rest of the test. Okay, find the maximum shear stress and tensile stress in the shaft. That's just TR over I. You've got T, you got the radius, which would be half the diameter, and you got I, so it's 2.12 megapascals. That's both the maximum shear and normal stresses. Now, the shears act on the 0 and 90 degree planes. That's the maximum shear stresses, so that's planes A, B, and C, D. The normal stresses act at 45s to that. Now, when we build the biaxial element for this, we're rolling the shaft up as shown with 720. That will correspond to a shear stress on that side like that, so it goes the opposite direction on the far side. The other two meet in the middle, or excuse me, at the corners they meet. So you can see that these two stresses right here will combine and get you a normal stress pulling out that way, whereas these two on this side will get you a normal stress pulling that way. There we go. Okay, so the plane for maximum tensile stress is GH, this plane right here. Okay. All right, the next one there, we want to convert the RPM, which is revolutions per minute, into radians per second, 141. Multiply that by the torsion that you're given. That will get you power in foot-pounds per second. You can convert that to 54 horsepower. The torsion then is just the force, which would be the weight, times the offset distance from the center of the shaft, which would be 7 inches. Convert the torsion into pound inches. And that equals the weight times 7, so the weight is 360 pounds. The last one here is indeterminate, so TA plus TC is 1500, the applied torsion. And then you know that the angle measured from A to B is the same angle as is measured from C to B, and it's TL over IG. So put in the unknown TA times its length, 0.9, divided by I, divided by its G. Do the same thing for C, TC times its length times I, divided by I, divided by G. I just canceled the i's, they're the same, and I canceled the 10 to the 9s, and I get that 3TA is TC. So TA plus TC is 1500. Plug in the 3TA, it's 4TA is 1500, so TA is 375. TC is 3 times that, 1125. You can then find the angle either by using from A to B or B to C, or C to B. It's the torsion times the length divided by I divided by G. In both cases, you get the same answer, which you should. That's a good check on the work above, 0.00147 radians.